Uh, welcome. I'm Inessa Paulson, Open Source Program Manager at OpenTeams and Head of Open Source Architect Community, the host of today's event. A few words about the OSA community. We are a trusted circle of open source builders who are shaping the future of technology and digital intelligence. Our members are the human network behind many foundational and widely adopted open source projects. The roles and responsibilities of our members within their organizations may vary. Software architects designing enterprise-grade solutions with open source, maintainers keeping critical infrastructure running, educators training the next generation of practitioners, founders and CTOs building open source-driven startups and enterprises, academics connecting research with real-world impact. But at the core, we are a community of open source builders. So if it sounds like you, I invite you to join us. Connect with a trusted network of peers and experts who build with open source. Grow through our professional development program, including training, networking events, certifications, occasional conference tickets. Explore customer and partner acquisition opportunities, and recruit top technical talent through the POSI Alumni Network, our pipeline of trained open source developers early in their careers. And how to join? Use the QR code if you have a phone next to you. And we also, if you know someone who builds, maintains, teaches, or leads in open source, please invite them to our network. And you can learn more about the OSA community at openteams.com/openteams-communities. And I will post that link in the chat just in a minute. And just a few words about the sponsor of the OSA community, OpenTeams. We believe software and people are at their best when open. OpenTeams is committed to helping organizations, big and small, break free from proprietary SaaS while sustaining the open source ecosystem that makes innovation possible. OpenTeams is helping organizations leverage open source technologies effectively, protecting and sustaining the ecosystem through responsible funding and partnerships. We are advocating and building a decentralized, resilient, and innovative AI future for everyone. And a few projects that we maintain and build: NumPy, SciPy, PyTorch, Numba, Apache Spark, IPython, scikit-learn, and many more. Each project represents countless hours of volunteer labor and collaboration, and our goal is to make sure that their work is recognized, sustained, and funded for long-term success. And with that, we will move to the topic of today's event, and we will have a quick switch of slides. Okay, just a moment. I lost you all for some reason. Oh dear. Can anybody use audio to let me know that you're still?
We're still here.
Okay.
Yes.
All right.
I would, if you have slides you wanted to share and forgot, just send you a note.
Okay. All right. And now I see you. Yes. Okay. Too many screens open all at once. Okay, good. Well, Ehsan, feel free to switch to the slide deck that you're going to use first.
All right, sounds good. Can you guys see my screen and hear me well?
Yes, we can.
Yes, very good.
All right. Thank you everyone for joining. Very excited to be here, talking to open source architect community and the folks who maintain critical software, as Inessa mentioned. I'm Ehsan Totoni, co-founder and CTO of Bodo.ai. I've worked on democratizing high-performance computing for all developers for a long time, and Bodo software is what we have built to achieve that, and this is an example of, or the latest version of that work. So Bodo DataFrames is an HPC-based drop-in replacement for Pandas that we'll discuss today. With me, I have Scott, one of our great engineers working on the Bodo DataFrames, and he will show some demos, cool demos as well. And would love to get your feedback and thoughts and questions during this presentation. So Bodo is a high-performance data processing engine in Python. You can compare it to things like Spark, Dask, and so on. It's open source. We went open source earlier this year or late last year, and you can install with pip, conda, and for the Bodo DataFrames library, all you need to do is change your import bodo.pandas as PD. That's all, and it will give you parallel computing with the MPI automatically. So MPI is message passing interface, the standard way of running parallel applications on supercomputers, basically. And it wasn't used in the data world before Bodo because it's complicated, but we believe we have simplified it, and the user doesn't even need to know it exists. We only mention it because of the performance that it provides. So you get proper parallel computing, we believe, for the first time. You get JIT compilation of custom code, which is our original technology that I will talk about. And you get query optimization of relational operators that we will demonstrate as well. Bodo has a SQL engine also called Bodo SQL, open source. It has very exciting features. We can discuss it if anyone's interested in SQL. In today's world, because of AI, Python is a lot more popular, I believe. And Bodo, supports all different kinds of storage and formats that you would expect from a data processing engine. Right. So in terms of agenda, a little bit of motivation, and then we'll talk about Bodo, internals of it, how things work, and show some benchmarks and show some demos. Pretty kind of simple agenda, and would love any questions at the end. So in terms of data infrastructure, obviously handling large data and processing large data has always been difficult, but in the age of AI, it's a lot more challenging even. So if you have an AI application, you need to have some data, collect some data, store somewhere. You need to process that data to get it ready for your training. You need to do training and then inference, right? The four main stages. And the problem is that, you need a lot of data. It's hard to manage it. And the infrastructure gets very complicated, especially because you typically have different tools for data processing and AI training that don't fit well. And because of these, the pipelines get too slow, run out of memory, all sorts of things break. So we are trying to address these challenges with Bodo as well. So on the data side, we are focused on Iceberg table format. If you're not familiar, we'll talk about it at the end a little bit, which is standard kind of way of storing database like tables on data lakes. And we have made it as simple as read and write a Parquet or CSV. Just pd.read iceberg will work, or dataframe.to iceberg. And we contributed the sequential version of this to Pandas. Will come out in Pandas 3.0, which is delayed for some reason, looks like. But with Bodo, you get a scalable version with the Bodo engine. So that's on the data storage side. For data processing, obviously, is our bread and butter, all sorts of data cleaning, ETL, feature engineering, custom transformations. Bodo is built to do all of that. But also, we have added a new Bodo AI toolkit, which is Pandas-like APIs for AI functionality. So the same way you have series.dt for data computations, we have added series.ai. Tokenize, LLM generate, kind of calling LLM, and so on. We'll very briefly talk about this as well. On the model training side, we have added very tight PyTorch integration. So, and we'll show some code a little bit that you can go from raw data, process it, and feed it to PyTorch in a single Python script. You don't need separate Spark clusters or complicated pipelines to achieve that. And on the inference side, again, the AI toolkit supports that for embedding and calling LLMs, but also for vector databases, we have added DataFrame.2 S3 vectors, for example. That makes it very simple to store S3 or query S3 vectors as a vector database, which works very well, looks like. So in terms of background, typically a data scientist, data engineer working with data in the Python world, you will have some parquets, CSV files, and write pandas, right? So that's, the basic workflow is very simple, easy to use. But the problem is that, so even though this is very easy to use, you can express complex code that you wouldn't be able to easily express in something like SQL or Spark or something else. It's very easy in Python and Pandas. We have the PyData ecosystem with a lot of tools being compatible with Pandas. You have notebooks and all tools for Python development working very well. But standard Python is single-threaded and single node, so it can get very slow or run out of memory. And if you have a lot of data, accessing those in the cloud is very difficult, and managing the data, the files, and the schemas is very difficult as well, which we'll address with Iceberg. So to get started, let's just look at some code to get a good sense of what Bodo is in a concrete way. Then we'll come back and talk about the internals of Bodo and how it works. Scott will provide.
Hello, everyone. My name is Scott Routledge. I am a software engineer at Bodo working on DataFrames. And I'm going to be demoing Bodo DataFrames as a drop-in replacement for Pandas. So we use this example of a representative data engineering or ETL style workload where we are going to be reading from taxi rideshare data in New York City that's stored in Parquet files and enriching this data set with weather observations from Central Park, doing some custom transformation and aggregating the data set to create some representative trip summaries. So we have the code for this workload below. We like this workload because it has a lot of performance critical operations like reading Parquet files, date time manipulation, custom transformations via this series.map API, group by, sorting and writing Parquet files. So this is all valid Pandas code, and I will now demonstrate that if you change your import, instead of import pandas as PD to import bodo.pandas as PD, the code will still run and it will give you scaling and acceleration over pandas. So I'm going to set up my environment. And because we have this custom transformation, as Ehsan mentioned, Bodo does just-in-time compilation. So I'm first going to just run some trivial function just to load the compiler modules and then run the workload. When I tested this, it took around 8 to 9 seconds. It might be a bit slower. Okay, so it was 8.5 seconds. And since we are compiling this custom function the first time we run it, we can get even better performance the next time we run this workload because we can use the result of the compilation from cache. So this is just demonstrating that. It was actually a little bit slower, I think, because I already populated the cache in previous runs. And then we can run the same exact workload in Pandas. So notice now we are changing the import back from bodo.pandas. Now it's just pandas, and we can run. You can see from the below, it took about 89 seconds to run. So I don't know if we have time to run the full thing, but maybe we can just let it run and go back to the presentation and kind of check on it later to see when it's finished. So yeah, handing it back to Ehsan.
Great. Thank you, Scott. Find my window again to share. I don't know where it went. Yeah, it's here. Do you see my slides? I think
Not yet.
something. Not yet. I don't know where. Oh, it was full screen. You need to get out of full screen before you share it. Great. All right. So how does Bodo work that's different than others? So if you want to go from Pandas to something scalable, there's Spark, Dask, and others. And unfortunately, there's a lot of implementation complexity. You have to rewrite your code basically in a lot of cases. And also the performance is quite poor. There are task-based models, execution models with a lot of overhead. Um, and the way they work is there's a driver and it sends tasks to executors. The executors run those tasks and they have to go to the driver for any kind of communication. And this is a driver executor approach that has a lot of overheads. We have a research paper on this if you want to learn more. With Bodo code, we want to compile the same Python code, either compiler or the DataFrame library is sort of a compiler too. And you will get a single program, multiple data way of parallelism. All the cores are actually running the code and communicating efficiently usually with collective communication with MPI. So it's actually truly parallel and done the right way versus just kind of hacky tasks floating around. So with Bodo, drop-in replacement, don't change the code, and you get HPC execution from for free anywhere you want to run any number of cores, laptop or clusters, right? And obviously other optimizations, JIT and query compilation. So that's the Bodo approach that's quite different than others. Bodo DataFrames, again, you just change your import, the same Pandas code. You get a database grade query optimizer. There are a lot of engines claiming to have query optimizer, but they don't have a lot of features. We'll talk about some of the features that the proper query optimizer should have. You get a JIT compiler automatically. You get MPI-based execution, and it's a streaming execution through operators. We'll talk about it. Sometimes you need to spill to disk if streaming, you can't stream the operator fully, like a join on the build side or group by build. So there's spilling to disk to support that, just like a database. And if something is not supported, it will fall back to Pandas. So your code doesn't break, right? That's a quick overview. But to see how it works, it's actually lazy evaluation to be able to optimize. So when you do pd.read parquet, no read actually happens, and a plan node gets generated for read that's stored in the variable. So there's a plan in this variable df. The data doesn't need to go to Python, so it's lazy. It doesn't do anything. You do some computation. In this case, these are kind of projections in database terminology. And again, the plan gets updated and has some more computation on top of the original read. You do a filter, add it to the plan. But when you write to storage, obviously the data has to be materialized. And the plan gets sent to workers, optimizations run, and they will execute the plan. So your user process is standard Pandas, but there are some workers doing the work in the background, optimizing the plan and actually running the plan when necessary. Right? The later, the better, so it has more context for optimizations. So an example optimization of the query at the query level is a filter pushdown that you always have in a database, and I believe you should have in any sort of data frame library as well. So in this example, there's a filter, but it's kind of late. So you read a bunch of data, you do some computation on some data that may get filtered out. Therefore, it's a lot better to push the filter down in the plan, meaning do it as early as possible during the read. And if the data is set up correctly, you may actually avoid reading a ton of files. And instead of a terabyte, you may read a gigabyte, right? If the data is partitioned properly. And you don't do extra computation on the data that will be deleted later. So this is a critical optimization that has to work really well if you're dealing with large data. And another important optimization if you're dealing with large data is join reordering. A lot of other data frame libraries and engines don't really do join reordering well. And I think it's a critical optimization. So when you have several joins, which is typical if you have kind of a star schema set up for your tables and data, you can a lot of the times run the joins in any order to get the same results. Right? But the order really matters for the intermediate table sizes that get generated. And a bad join order can be hundreds of times slower or thousands of times slower. This is a really critical optimization in the database, like kind of operators. So here's an example. You have 2 joins, 3 tables, and if you do the first order, a lot of keys match. There's a massive table, and this join, you need to put a massive table in a hash table for the build side of the join. That will get very slow, spill to disk, run out of memory, all sorts of issues. But if you reorder the join, it may filter out a lot of the rows, and you may get very, very good performance. And query planners use dynamic programming and cost-based cost estimates to figure out the right order. And it's quite difficult to do. So you need to make sure your engine has a good query plan. And good databases obviously do, but not the Python data frame side. So that's about joins. There is another critical optimization for dealing with large data, which is having join filters. So you may have a query tree that's quite deep and has a lot of complexity. But one side is the build side of the join, and the probe side has a lot of stuff going on. But when you do the build side, you will know that only keys between 10 and 100 or 10 and 1,000 will match, right? So on the probe side, anything you do on other keys is useless. So you can actually filter out all of them. So join filters get generated to filter out data as soon as possible on large tables. And I have seen billions of rows turn into millions, so like 1,000 plus times speed up just because of this optimization. And it's critical. It's tricky to implement because it's not a relational tree anymore afterwards. So it has to come at the end, and it has implementation complexity. If you want to look up more details, it's called sideways information passing in kind of database research terminology. And not many data frame libraries do it, but kind of good databases. I think Snowflake does it. I'm not aware of others too much. Snowflake has good support, so we have added this here. So that's about query optimization. We actually took some code from DuckDB query optimizer, proper database, and customized and built our own optimizer to make sure it has a good foundation. So we are very happy with it. Bodo SQL, it's based on calcite database framework. So a good foundation for what we have built on the optimizer side. So on the execution side, when you have a plan like this, so this is an example we're going to go through for demonstrating execution. It's called vectorized execution in the database terminology, but it's basically streaming batches of data across operators so you don't run out of memory, and performance is better cached locality. For this code, it's just reading some Parquet file, some computation, group by and write to another file. And the plan looks like what's on the right. There's a read at the bottom, projection, some aggregation, and write to file at the end. So the way this gets executed is the logical plan become a series of execution pipelines. Right. So a pipeline is where a batch of data can go through without interruption and without any synchronization, which is not always possible. In the case of aggregation, you have to see all the data before you can continue. Therefore, it's a pipeline breaker, and you will get 2 pipelines from aggregation. So you have to read data, do your projection, update the aggregation table, hash table, and then you have another, when it's done, you have another pipeline that reads that table and writes to the Parquet file. And this is in the database terminology called push-based execution model, where the operators pass data along instead of the top operator pulling the data from the bottom operators. Better performance, but more complex to implement. We decided to do it because the performance is critical here and working out very well. You can look up more details. The CMU database lecture series talks about it very well. So that was on the sequential side. On the parallelism side of things, we have asynchronous message passing between cores in these pipelines. So obviously for aggregation, the keys that are the same need to be on the same core, and the communication needs to happen. We use asynchronous MPI messages that work in concurrently with computation. So they overlap. So we overlap communication and computation using these async messages. You are not going to wait for networking to happen before you continue. So that's really useful for performance. And the workers are independent. They don't need to synchronize. They can have different number of iterations, different number of batches. And when the pipeline is done, they can synchronize because they're out of the loop. So that's at a high level what we have built on the DataFrame side. And here's a comparison table from one of our blog posts. And I think the three important dimensions are how easy is something to use, how good is the query optimizer, and how well does the execution work in terms of performance and scaling. And for ease of use, we are fully Pandas compatible. That's our goal. And I think that's the easiest to use because everyone knows Pandas in the Python community. On the query optimizer, we are making sure it's a database level optimizer, not kind of a toy optimizer you may see in some other systems, and basic rule based. And on execution, the best possible HPC level execution. So that's we are trying to combine best of three worlds, basically. Others don't have a lot of these aspects. The API may be new, some SQL-like wrappers in Python, like Polars and Daft. They may not have an optimizer or very simple heuristic rules. They may not do good high-performance execution. None of them do, basically. Only Bodo has the HPC level execution. So this is a good reference if you wanted to learn more. And I would be happy to explain more the details. So that's about Bodo DataFrames. Let's talk about the Bodo JIT compiler and how it works. So Bodo DataFrames, we built it to be drop-in replacement for Pandas, very easy to use. But for getting the best possible performance, initially we developed the Bodo JIT compiler. So you can use it not just for user-defined functions, but standalone for the whole computation. And it's, the workflow is very similar to Numba, for example, and it's actually built on top of Numba. It compiles Pandas and NumPy operations to a binary with a MPI communication automatically, as if an HPC expert rewrote your code in MPI C++, right? Just like the supercomputer code. If you have a lot of custom code and you want the best performance, you can try this. And I will talk about some of the limitations and the challenges too. So in terms of what kind of the word compiler may remind you of a C compiler or something like that, but Bodo JIT compiler is very different. We call it inferential because it actually understands the structure of the code, optimizes operations at the high level, and parallelizes the operation. Your C compiler just turns something to a binary. It's very simple. But the Bodo compiler actually optimizes and parallelizes at the algorithmic level, which is something new. It's sort of a domain-specific language compiler for Pandas and NumPy, not really a low-level compiler. So this is kind of the new concept that we have developed. And compiling Python is very challenging because there are no data types. The objects may change data types, and you can't even analyze the code, let alone get into a binary at the end. But the way we have addressed this challenge is a lot of techniques. A key one is type inference to even be able to get started compiling. And it's an iterative transform-based typing, meaning that you run type inference, and if it fails, you try to, given the partial data types that the compiler has been able to gather, try to fix the program, transform it to an equivalent version that's compilable and can continue typing, right? And if it couldn't figure it out, obviously it will fail. But a lot of the times in practical codes, it will succeed after this transformation. So I'll show you an example here. So if you have in-place operations on the left, this data frame changes its schema, and schema is part of the data type in Bodo. So it's not, the code on the left is not compilable. It also creates a new column A2, assigns a value, again, changes the schema, not compilable. But these are very common operations. You can't, in typical Pandas code, no matter how much we may dislike in place, it exists, and we need to be able to handle it. So this transformation, after seeing that there's a data frame, given the partial data types, that has this method with in place, it will replace that operation by assigning it to a new data frame. And for a new column, A2 does the same thing. Obviously, this is not possible in all situations. What if the original data frame, in-place data frame, is used somewhere else? And in the compiler, the way it works is it makes sure the in-place operation post-dominates the creation of the data frame, meaning that every program path from creation of the data frame goes to that method. So if we change that data frame and create a new one, the original data frame doesn't leak anywhere, and the side effect doesn't get seen, which is, I have never seen a user code that would violate this, maybe once, and pass however many years. So typically it does, but we need to check to make sure the compiler is correct, and it produces equivalent code. So that's about iterative typing to enable. There are a lot of optimizations as well. A key one for NumPy code, especially for Pandas as well, is fusion of loops. So when you have an expression A times B plus C, where A, B, and C are arrays and a lot kind of vectorized computation, in Python or NumPy and Pandas, you will do operation by operation. A times B creates a temporary, and then add it to C. With Bodo, first of all, we need to recognize parallelism of these operations. So the way it happens in the compiler is a concept of we call parallel for loops, or par-fors. We contributed this in Numba, the threaded version as well. So it first gets converted to par-fors, and there's a temporary T here, which means the data gets kicked out of caches and registers and then comes back. So when you fuse that loop, the temporary goes away and the computation happens in registers. And it's very critical for performance, sometimes 10 times better performance. So this is another example of compiler optimization that Bodo does. There are a lot of other analytics kind of code optimizations as well. Just another one here is when you just to show you the patterns that are possible. Let's imagine you have a series bottom left, and you're comparing it to a scalar string value, right? A string series, a scalar string value, very common, right? Find the values in the string, and typically the string is stored in a packed representation where in Arrow, for example, or other high-performance systems, including Bodo, all the characters in an array and their offsets in the character array specifying where its string starts, right? So when you have this for loop top right, it will access this array, and the vanilla code will create a scalar string out of this array and compare to the other scalar. But creating that scalar is basically an allocation to put the character somewhere, and its allocations on loops is very, very slow. So Bodo will recognize this pattern and replace it with an in-place comparison call that doesn't create that scalar, and the performance is 10, 20 times better for things like it. So this is another example of optimization that a good compiler can do. But with JIT, obviously, there are limitations. Compilation takes time, and if you have a massive code base, that changes. There's compilation caching, but still, the first time might take time. It doesn't support all Pandas and Python APIs, so it's a subset, just like Numba. We try to cover the basics, but there may be something missing. And fundamentally, there are things that are not compilable. If a variable truly changes data type and the compiler can't fix it, or you have functions that are not resolved in the middle column, things the compiler will fail. So the code has to be relatively clean for the compiler to work. So therefore, the data frame approach, starting with that one, is recommended to make sure your code works and it's easy to get started. And you can look at the compiler when you have something that fits the need. In terms of benchmark, this NYC example is quite nice. NYC taxi data set, because it's public and it's real data and looks very interesting, a lot more interesting than some other synthetic benchmarks. And we compared to DAF, Polars, PySpark, Dask, Modin on Ray, and both the DataFrames and JIT compiler are a lot faster than others. And it's all open source. You can rerun the benchmark with a run script that we have developed and reproduce these results. On the left, it's a single node. On the right, it's distributed. Pandas doesn't exist here because we couldn't get Pandas to work on this data set size, no matter how big the cloud instance was. So that's another interesting indication of Pandas limitations. I mentioned some of the AI extensions, and just to summarize what they are, you can look at them if you're interested. They will run the AI function on all the elements in parallel and stream the data and make it scalable if you want to do batch inference, batch embedding, and make it really easy to work with AI tools like PyTorch as well. Feel free to take a look if you are interested. And this is the PyTorch example, a few methods to connect your data with PyTorch and run it in a distributed cluster. And it's in our GitHub repository. A little bit about Iceberg. I think the Python community needs to embrace Iceberg more, because if you're managing raw files in your data lake, you can't track the changes. Object storage is slow for a lot of files. Schemas may change. The schemas always change. Some column comes and goes or gets renamed. And with Iceberg, you get database-like features like ACID transactions, schema evolution, efficient metadata pruning to load only the data that you need without hitting some of the limitations of object storage. So I recommend looking at it. And in Bodo, as I mentioned, read Iceberg to Iceberg, very easy, just single line. You will write to Iceberg on your just files and leverage Iceberg. And then you can have more complex Iceberg setups if you're interested for more scalable, larger scale and complicated use cases. Again, for Iceberg, it solves a lot of problems with Parquet data sets. You don't need to list files anymore. There are metadata files specifying those. Statistics are better. I mentioned join ordering. it's very important to have good statistics for join ordering, filter pushdown, some of these optimizations, and it will handle the schema changes that usually occur in large data, significant data sets. So with that, let's go look at a little bit of demo on these new cool features, and we'll conclude and go to questions afterwards. So Scott, back to you.
Okay, thank you. So as Ehsan mentioned, I'm going to be continuing the demos with some of the AI toolkit examples as well as Iceberg. But first, I wanted to just come back and touch base on the first demo that I ran. See the Pandas result finished. It was about 62 seconds, which is about an 6x speed up. And this example, I forgot to mention, the data set is about 40 million rows, so a much smaller version of the benchmark that was shown on the previous slide. And I was running it on 4 cores. So with 4 workers, we were able to get a 6x speed up over Pandas because of the query optimizer as well as the parallelism benefits. So going back to the AI toolkit example, so Bodo has these functions for extending Pandas. So these are not in Pandas, but they're Pandas compatible. So they take data frames and series, and therefore simplifying and scaling common AI workflows. So this example is storing vectors in a vector database and querying that uses Bodo AI Toolkit as well as S3 Vectors, which is a vector database that's part of AWS S3 service. So if you have an AWS account, you can follow this tutorial to set up a vector bucket and then run this demo yourself. This notebook is on our GitHub if you wanted to try any of the demos here yourself. So in this example, we are going to be creating a vector index using the AWS Python SDK, and then we're going to be writing some vectors that are going to be derived from these movie summaries, which we're going to create a data frame and then call this AI.embed function, which is going to use the, in this case, OpenAI model to create vector embeddings for this series of text. And as Ehsan mentioned, this API is parallel, so we're processing multiple requests in parallel, and also is uses the streaming infrastructure that we talked about as well. And then we can also write to our vector database using this toS3 vectors function. It's the same story as the AI embed. It's parallel, it's streaming, so you can stream your vectors from your sources to the vector database without worrying about running out of memory, since vectors can take up a lot of memory. And then lastly, we can query the vector database using this query vectors function, which again is streaming and parallel on the back end. And then switching gears to Iceberg, we have the demo of Iceberg time travel feature. So this lets you query your data set and your tables at different points in history. So as your data set evolves, you can ensure that the results of your experiments or your workloads are reproducible. And it's also great for things like compliance as well. So in this example, we're just going to create an Iceberg database locally using this directory catalog, although you can use any REST catalog like S3 tables or Polaris has. And we're just going to read some data from the taxi dataset Parquet files and write a few rows to an Iceberg table. And we're using this toIceberg and pd.read Iceberg APIs, which, as Ehsan mentioned, are going to be available in Pandas 3. But for now, we have them in Bodo, and they are, again, using the parallel streaming infrastructure that we talked about. And then we're going to read another Parquet file and write some more rows to it, so we can see our table is now larger. And we can use PyIceberg, which is another Python package is an optional dependency of Bodo to query the history of our table, and we can see there's 2 events in our table's history. And we can use the snapshot ID or the timestamp to go back and query our table at these points in time. So this is what we're going to do now. We can read our iceberg table from the first snapshot where we wrote the initial 5 rows, and then we can go and read from the current snapshot and see our table as it exists today. And then you can combine this with more complicated workloads. So this example, we're just getting the mean of a trip column, and we can see how this value evolves as our data set changes. So those were the demos that I had today. Happy to open it up now to any questions either about the demos or anything that we talked about in the presentation.
I'm happy to go first. Well, first of all, Ehsan and Scott, thank you so much for your presentation. I know the Bodo team has been collaborating with OpenTeams for several years, but only recently I had the opportunity to experience firsthand at the last conference the technical solutions that you're building on. The moment I heard HPC Pandas optimization, I knew I needed to have you as our speakers because a large number of our community members do data analysis with Python. And, there's, I'm sure those of you who are in this camp, there's this new cool kid in the data science space with a polar bear in its logo, but Pandas remains the default tool for many data scientists. And it's great that there are solutions that help make day-to-day lives of data scientists who work with Python a little easier. So the question I have is very much aligned with what I do on day-to-day, and that is not data science, it's open source maintenance, development of programs that build out the pipeline of contributors to open source. And you mentioned that Bodo DataFrames was open sourced in early 2025, so pretty recently. And by the way, congratulations on the sleep. As a passionate open source advocate, I salute you. I am curious if you experienced any change in adoption of Bodo DataFrames and maybe you had to adjust the roadmap for the project.
In terms of open source, I'm a huge advocate as well, but as a company, a lot of things have to come in place for that to happen. So just a little bit background, the Bodo JIT compiler wasn't as easy to use and difficult for kind of adoption for a lot of people. So that we fixed that was a significant project. And we built Bodo DataFrames actually mid this year. It's very, very new or earlier this year, which is very easy to use and good for adoption. So these needed to be in place before open source and trying to accelerate adoption. But to answer your question, there is a graph of downloads for pip, and pre-open source is kind of flat, then it shoots up. So open source is very important for adoption, and we are starting to get questions and feedback, which is really great. And we get forums like yours to discuss it, with the open source folks. And it's open source is really good for innovation. Just no barriers for technical folks to discuss ideas, and helps you stand on the shoulders of giants, whatever you are building, because these kind of things are extremely complicated. So that's about adoption. What was the second part of your question?
I'm curious if you had to adjust the roadmap, as we call it in open source, if you had to prioritize or maybe start working on features that was not in your immediate plan for this project due to open sourcing and getting more feedback from stakeholders.
Absolutely. We love feedback from different folks, and we try to be very prompt and kind of Yesterday, someone wanted a feature, and it was it was added recently, but the release wasn't there. We just released, went through the release very quickly, so to enable them. GitHub issues, we have addressed them in a matter of days. So it's very important to engage and make sure the roadmap fits what the user community wants. And in this case, there are a lot of different things that can be done, but the feedback has been very useful to direct us. And we are still early, growing the user base, and looking forward to more feedback.
Oh, well, that's great to know that it's been a great start for Bodo DataFrames and the open source community. And this is something that not often mentioned, that accepting contributions comes with some workload for developers. So as a project and a company, you need to be ready for accepting those contributions. And I highly encourage everyone who is considering to open source their projects to make sure that you have infrastructure, you have the bandwidth on the team to communicate with external stakeholders, support them, especially if you're welcoming external contributions. And then maybe just a follow-up question, and then I will let other folks to jump in with their questions. What is the best way to start contributing to Bodo DataFrames?
Definitely, I have links on Slack and GitHub. You can get on our GitHub, just search GitHub Bodo. You'll get Bodo.ai, and you will see our Slack on our website and GitHub. Obviously, open issues on GitHub, reach out, send a message in Slack letting us know. It's better to communicate early what you want to contribute, what your approach is, what your design is, to get feedback, and we'll be very prompt. And then we'll work with you to get it merged as soon as possible. So just very standard communication channels of Slack and GitHub. But I would suggest, just generally as a suggestion, over communicate. The more, the better, right? And it's better to be prompt in open source and kind of communicative versus quietly building stuff.
That's a great advice, yes. And now I am going to open up the floor to the rest of the folks on the call. If you have any questions, technical questions, questions about contributing, something else you're curious about in the same space, data science with Python, this is a good place to ask these questions.
Yeah, I'll just speak up. Impressive, by the way. That's quite a bit of speed conversion and stuff. But I love your technique, the way you approached it. It was really good. I just wonder what some of the next challenges you think you're going to be able to solve with this.
In terms of challenges and roadmap, we are trying to get feedback. We are early phases of user feedback to see where to focus on. It could, some areas include obviously more Pandas coverage, and there are areas of Pandas that are kind of challenging to support. If you want to focus on the financial application, time series applications, merge as of, that kind of time series merge. So there are these challenging features. There is a lot of other optimizations that could be done. I mentioned metadata and Iceberg. Make sure the optimizer works very well. So right now, a recent example is you have column pruning, but if you have CTEs, common table expressions, be able to support complex nested CTEs in column pruning. That happens in Python because if you have like a data frame object and you access it multiple times, it's equivalent to SQL CTE that you would have. So there are these challenging optimizations as well. There is extensions for AI and storage, Iceberg that we want to do. So a lot of things need to happen. Also, something we are looking into is a CPU-GPU hybrid execution because there's a lot of GPU interest and GPU use for data side. They haven't been used very successfully, I would say. But if the infrastructure is there, we can try to do interesting things. Given the fact that we have a compiler, we can actually turn vanilla Python in some cases to GPU code, I believe, So we would like to try that. And also there is the transition from other libraries. So if we provide PySpark APIs, it will make it easier to use PySpark code with Bodo without kind of going back to Pandas. Sometimes the Pandas code, so people write Pandas and then rewrite in Spark. The original Pandas code gets lost. So sometimes you have to support PySpark. So there's a lot of things that can be done that we are looking at and getting feedback to focus on. But it has to, the core has to work really well. That's always the focus of the project.
Nice job. That's really good.
Thank you very much.
Well, we are at time, but we'll take maybe one more question. So if you have a question, please use audio. And if you think of questions later, please post them on our LinkedIn feed. I shared links earlier. Okay, any questions? Anyone? All right. Okay, well, I think our Q&A is up, and I just want to thank you, Scott and Ehsan, again for your presentation, and also to our attendees. Thank you all for being here, for your curiosity, for helping shape this discussion. I will be posting the presentation on the OpenTeams YouTube channel soon, and if you missed anything or just want to revisit the highlights from today's presentation, keep an eye on your inbox, and let's keep the conversation going on LinkedIn. Thank you all, and enjoy the rest of your day.
Thank you very much.
Thank you.